Hello, hello, welcome. We have a special guest here. We have Professor Eric Snively of Oklahoma State University at the College of Osteopathic Medicine at the Cherokee Nation. And today he is giving us an exclusive, or at least an early version, of the paper called Hatchlings of Tyrannosaurus Rex and the Evolution of Dinosaur Reproductive Strategies. Walk me through what this paper's about, what you thought about it, and I know you've got some slides to share, so the floor is yours.
Right. Well, so the exciting part of this paper, one of them really is the discovery or rediscovery of some hatchling tyrannosaur material, including Tyrannosaurus rex, Gorgosaurus, and actually stuff probably from Nanotyrannus. And I'd like to walk you through the discovery and some of our findings from this. So I'll share the screen here and we'll get quickly into a PowerPoint presentation.
All right, I see the screen. I see some metatarsal 3, I believe.
Right, that's exactly right. So we have two third metatarsals, distal ends of third metatarsals, which is like it's a central bone in the flat of the foot, sort of up off the ground, distal to the ankle in tyrannosaurs. And this particular Tyrannosaurus bone, discovered by Tim de in the Badlands of the Frenchman Formation near East End, Saskatchewan. And he picked it up at a microsite called the Bingo microsite and brought it into the collections at the T-Rex Discovery Center in East End. And one day, Nick Longrich was going through the collections looking for fossils of small dinosaurs, and he discovered this thing. And we noticed that it had a porous external texture, which seems to occur in juvenile dinosaurs. And Nick was really excited that it might share characteristics of tyrannosaurs. And so we looked closely at it. So here we have front, back, sides, and the top. There's a section where it sort of is at the top there. And so it's a broken specimen. And we noticed that very few dinosaurs have this sort of triangular look to their third metatarsal in proximal cross section. You're sort of looking down on top of the end of the metatarsal near the ankle. Only tyrannosaurs have these sort of technical features here. Only tyrannosaurs. And from the late Maastrichtium of North America in these beds, only Tyrannosaurus has this pillar, this solid element in back of this otherwise slender bone. That's interesting. It has this big sort of pedestal here. The other bones come on down on the outside. This was a great clue that this was a Tyrannosaurus rex, and that even if it was a juvenile Tyrannosaurus rex, very early on, they were built to, I'm going to get a laser pointer here. They were built to uphold all their weight on the central metatarsal by this big pillar here. So the tiny bone, I'll give you guys a hint how big it is. It is less than 1 centimeter across. It's a little over 8 millimeters across. It's just maybe 10 centimeters long in life. That is tiny. There you go. And I'll show you an image of it a bit later.
That is so skinny.
So only T-Rex has this big pillar here. In Sue, it becomes a little different. Sue's really giant and does weird things. And so this is the central of the 3 interlocking bones of the flat of the foot of Tyrannosaurus rex. So here's Tim de and here's me. And I'm actually holding this little metatarsal in my hands here. Of course, you can't see it. It's just so small. And so if we look at the metatarsal of an adult T-Rex, here it is. This is from the Los Angeles County Museum of Natural History, or the Natural History Museum of LA County. There's our little bone, the same length as this big adult T-Rex, and it matches absolutely exactly if you compress it just enough. So this was pretty wild that we have this allometry, this changes in growth with body size. But remember, this little baby T-Rex had a big giant pillar on the back of its metatarsal. When it grew up to weigh 10 tons, it was all ready to go from the size of the time it was a hatchling. So what we did was sort of figure out from the size of this bone, the size of what it was like in life. And the Royal Saskatchewan Museum has a wonderful exhibit around this little T-Rex and Scotty, one of the world's largest T-Rex. And so that's where that bone is in the skeleton of the animal. So this is actually a really good model in a lot of ways. The neck could be a little more compact. That's okay. I study necks. But it's actually really good in proportions and in every other way. So we had this bone. We knew where it was from. We knew who it belonged to. And we scanned it on an atom smashing machine just up the road from the Royal Saskatchewan Museum. We scanned it in a synchrotron in Regina, the Canadian light source synchrotron. X-rays from electrons moving around in a circle passed through this bone, and they revealed spaces within the bone and the actual bone mineral involved. So synchrotron reconstructed blood vessels here on this side of the bone and on this side of the bone, which is the front part, and on the other side, showed us that these vessels were pretty big towards the sides. This means that the bone was being affected by loading. It was being affected by really strong loading, probably from running around, not the kind of thing you see with the bone just twitching around in an egg. And my former student, Dr. Brenna Hart, figured out what the heck is going on with these big vessels. So Brenna is going to reveal everything about how this occurs. So there's the front of the bone, there's the sides of the bone. Ligaments were pulling on the bone from the outer metatarsus. It was running around. And not only that, Nick Longrich is really good at, he has an amazing search image for features of small specimens in collections. And Nick found a lot of tyrannosaur teeth at the American Museum of Natural History and elsewhere were really, really tiny, millimeters big. And these teeth were actually pretty thick for their length. They were worn, the teeth were worn. And so our reconstruction by Raoul Martin of this baby T-Rex feathered, which is nice, it's jumped up on, looks like a Torosaurus type Ceratopsian. It's jumped up towards a dragonfly, but it's not looking at the dragonfly. Look at its eyes. Its one eye is craning that eye way over. It's looking at you. These animals with their worn teeth and their hunting ready ligaments in their feet were probably eating small vertebrates. They were eating animals with bone. They were biting into bone, just like the giant adults. This baby T-Rex is eyeing you up. When it gets a little bigger, when it's 3 years old, it's about the size of a lioness, it's going to chase you down. And it's going to gouge into your bone, just like the big adults were doing to Triceratops. That's sort of how we're interpreting all this. So that's sort of part of the excitement of our discovery. We also have a really great element of a baby Gorgosaurus, another kind of tyrannosaur, probably a little bit skinnier and smaller when it hatched. And that animal is kind of more on the edge between being an embryo and having the morphology of what we consider something running around. We're pretty sure it was running around, but it has features of its histology that point to the ambiguities, the difficulty of determining whether something was in the egg or not. This little baby T-Rex was out of the egg. It was running around. It probably could have hopped up on your lap. You could have pet it. Would have made a really nice pet for a while. And when it got older, it would have bitten your head off. So that's sort of our discoveries and our interpretations. And you notice this T-Rex is pretty small. Another big part of our paper was a thought experiment. If we have the size of a hatchling based on some mass estimates, based on the size of the bones we were looking at, it would have hatched out of an egg that was a certain size. And a T-Rex of a certain size would be able to lay a certain number of eggs of that size. So we took this as a thought experiment to say, what sort of egg size or clutch size might an adult T-Rex have? So this is going sort of way back beyond the size range of T-Rex that we have, but it gets us thinking. If we find a clutch of Tyrannosaurus rex eggs, how many eggs would we expect to find? It gives us a hypothesis based on some extrapolations, some very serious, large-scale extrapolations from size regressions and pretty good size estimates for this little animal to the size of the eggs the T-Rex might lay, the size of the clutch it might have, and what kind of parental care it might have engaged in.
When were you convinced it was a T-Rex? Because that's just the distal part of a third metatarsal.
Right. So, first of all, when Nick discovered the bone, his profane excitement reverberated throughout the halls of the museum. Nick was pretty sure he'd found a hatchling T-Rex bone. So when I first realized what it was, Nick had showed it to me. I went down and took a look at it. And I did a master's degree on metatarsals of carnivorous dinosaurs. And tyrannosaurs have very, very distinct features that separate them from some other dinosaur with kind of similar metatarsals, very different from ornithomimids or troodonids. Um, the kind of asymmetry that they have and sort of the depth of some of their ligament attachments. The curvature, the distal end of their bone and side view is very different from in other dinosaurs with this, what we call it, arctometatarsalien condition. So I instantly recognized that, okay, yeah, this is a tyrannosaur. Um, and when I turned it around, I realized this is a Tyrannosaurus because it has that pillar. So Daspletosaurus has a similar kind of pillar that's narrower, relatively narrower. Um, but T-Rex, as we say in the paper, Tyrannosaurus was the only really big theropod in the very latest Maastrichtian Hell Creek Frenchman Formation equivalent beds. The Nanotyrannus specimens that we're seeing now do not have this big pillar. So we've really found that out later, and also really cool. In the Royal Saskatchewan Museum, there is the metatarsal of a 3-year-old T-Rex. We could tell right away when we synchrotron scanned it that has that pillar. So we have this continuity from hatchling to a 3-year-old, about the size of a lioness, so 120 kilograms or so, a small lioness, up to 5-ton adults, and then Sue gets weird. Sue's really big. So I knew right away it was a tyrannosaur, and Nick and I actually scanned it on a micro CT scanner to see if there were any growth rings. And we didn't see any growth rings right there, but we really had to scan it on the synchrotron to make sure. Greg Erickson, he's one of our authors. He just looked at the proximal end. He said, "Yeah, there's no growth rings here, and it's not embryonic either." So Greg really knows histology really well. So it was cool discovery, cool corroboration from several sources. So I corroborated for Nick. Greg sort of corroborated its age for us. Um, and it was pretty cool and exciting process of discovery. And Nick discovered it, I think, in 2008 or 2009, and we've been at it ever since.
Wow. Well, I suppose in a way you have to get it right the first time because T-Rex is such a high profile animal and you have now produced a baby, which I got to say, the baby in your illustration is the size of a house cat. I mean, it is adorably cute and small. I thought that what a cute pet this would make. It would be, the people that have snakes would have one of these for a little while. And then problems would start setting in, I'm quite certain.
You'd end up like Daenerys from Game of Thrones, where you end up with a cute little ravenous reptilian slash avian beast uh, that turns really big, and hopefully it would remember you as its caregiver when it got that big.
So now that you found this, I'd like to point out to the world that this was discovered in a museum drawer.
And just to reiterate, like you said, Nick found it in museum collections, and it goes to the importance primary discovery in the field, looking at microcytes, looking at small animals,
The-
repositing these fossils properly in museums, and having an open eye and open mind when you're searching through collections.
You showed, I think it was like 5 characters that make that a Tyrannosaurus Rex. There's not just one, like, oh, it's got a heart-shaped ventral centrum for an apatosaur. No, you have multiple characters corresponding, and you clearly delineate what they are, and you compare them to the other theropods. And I left thinking, all right, yeah, that's a Tyrannosaurus. That's really cool. What are your thoughts on that little animal and what's going through its brain? How bright is it? Where does it fall in the intelligence line?
That's a tremendous question. So tyrannosaurs are coelurosaurs, so they had probably slightly bigger, various parts of their brains were slightly bigger than in other carnivorous dinosaurs. So there was a little more going on with them. Um, in a tyrannosaur this size, you'd see big optic lobes filling the endocranial cavity. You probably see impressions of the cerebral hemispheres. They kind of the space in the brain outgrew the size of the brain. That's pretty clear. Um, so it probably would have been, the analogy I like to make is, I have a lot of experience with raptorial birds. I like to think a baby tyrannosaur would have been just a little bit like, uh, sort of a little bit between a, um, a crocodilian or a lizard and a red-tailed hawk or an owl or something like that. So if there's food involved, all of these animals are going to act really, really smart, right? The baby tyrannosaur might have been slightly curious, maybe a little more so than in some other reptiles. Um, it's how it would react to you would depend on its sort of sociality. So Komodo dragons are a great example. Like my student, our friend Kyle Atkins-Weltman points out that Komodo dragons are sociable. Komodo dragons get along with you because they're born as apex predators. They scamper into the trees to avoid being eaten by adults, but they have no fear. And so this little T-Rex probably would have not been that afraid of things because as it grew up, it would not have been afraid of anything. So at least that's what I'd like to think. I like to think, yeah, it could have jumped up onto your lap and you could have pet it and everything. So that's one thing. And another thing is, um, it would have crunched through vertebrate prey. We might not expect that. We might have thought it would be going after insects and other arthropods and things like that. It probably did, but very quickly it would have transitioned to going after vertebrate prey and chomping into it.
And how heavy? You talk about a couple kilograms, heavy and long. And how old was this bone representative? And then back us up to in the egg and talk about the egg dimensions if you don't mind.
Right. So the the way we got sort of the size and mass of the animal was based on a decent assumption that the load-bearing area of the bones of the limbs correlates with the mass and the loading that the animal is carrying. And so we did regressions based on birds. And baby birds, some of them have actually pretty floppy metatarsals. They're fusing up, but they're uh, they're not necessarily as rigid as they are when they're really, really fused as adults. And so we thought we had a pretty good possibility that the loading that this T-Rex is bearing on this metatarsal was similar to what you expect of a bird of its size. The Tyrannosaur was actually better built for carrying loads and moving fast than a baby bird because it had flexibility within its metatarsus. So Tyrannosaurs could just do those sorts of things. So we got a mass of about 2.5 kilograms for an animal this size. It was less than a year old. We're not exactly certain how old it was. Nick thinks it was just a few weeks or months after hatching. And we extrapolated that back to hatchling size. So it would have been a little smaller as a hatchling. You cram that into an egg, and it's about the size of maybe smaller than a 2 liter bottle of, yes. So don't worry, I have a good prop here. So here's a 1.25 liter bottle of Diet Pepsi. So imagine this a little more rounded to be about 2 liters in size. And as we see in what we think are large therizinosaur eggs, it probably would have been narrower than it was wide.
So, and I have seen labeled in various places Tyrannosaur egg. Usually it's from Mongolia and it's probably Tarbosaur, but do we have any actual Tyrannosaurid eggs, or oid eggs for that matter, that are indisputably Tyrannosaur?
Not that I know of. So we think that tyrannosaurs might have inherited what's probably the ancestral condition for big dinosaurs, which is for a lot of big dinosaurs, which is more leathery sort of eggs that are minimally calcified. So Mark Norell determined this a while ago. He had one of the last papers he authored was on the ancestral condition for these dinosaur eggs. So it's possible that they were not calcified enough to preserve very well. Another possibility is that tyrannosaurs just laid their eggs in different environments. So as far as I know, we don't have any um, that we can confidently assign to tyrannosaurids, and maybe not tyrannosauroids overall. So for those who may be coming at this new, so Tyrannosauroidea is a larger group that includes tyrannosaurs and some earlier critters with front teeth like incisors, fused nasal bones on their heads with various tyrannosaur features. Then tyrannosaurids are the sort of classic animals like Albertosaurus, Gorgosaurus, Tarbosaurus, Alioramus, and so on. And then Nanotyrannus and its group might be outside that Tyrannosaurid group.
So when you came up with the size of the egg, you were using extant bird egg sizes, or what was the math? Because this paper, when you read it, everyone, get ready, because there's a lot of math. I screenshot different figures and brought it up so I could follow through. This paper is a tour de force of histology, plus some engineering and a whole lot of statistics. It was wow, I had to dust off, knock some gears loose in there, some WD-40. It's like, well, I haven't thought about this in a long time. But you did the math to get the egg size, and everything is based off of you phylogenetically bracketed things, by the way. Thank you. You didn't look at you looked at crocs and you looked at birds.
Right. So for the egg sizes, as you pointed out, Brian, we have regressions of egg size, and we're going from modern crocodilians, large ratite birds, down to small birds today, and uh, that regressions for egg size are going kind of beyond the data. Um, when we got the size of the embryo, then we can look at the size of an embryo in modern reptiles versus the size of the egg around it, and that helped us with a size estimate for an individual egg. Um, so the regressions of uh, egg size to clutch size that we might expect in a large tyrannosaur, those were where we really got into the sort of thought experiment aspect of it all. We have to thank uh, Evan Saita, one of our co-authors, and Pete Makovicki and Tomas Alecki, who really know what's happening on that side of things. And throughout it all, we were all quite skeptical. And so, like for egg size, we were thinking we really have to frame this uh, as pretty decent potential estimates for egg size and clutch size, what we might expect about reproductive biology in tyrannosaurs from these estimates. recognizing that the error bars are really big, and we are doing the best we can with the fossil evidence from the embryos, or from, excuse me, I should say, from the perinates and the hatchlings, the yearlings, and what we can do with regressions and comparisons with modern animals and their eggs.
And it was really cool to me. In a way, this paper was a classic science experiment. A thought, and you, each step was clearly defined with clear parameters, with the acknowledgement that there is an order of magnitude, in some cases, difference in size. And it was very candid as I worked, and you worked your way back modularly. Okay, this step leads to this, which leads to this, and then you went back the other direction. And when you came back into the clutch, so you got your egg size, then you estimated clutch size, and then you hypothesized, going back to my high school biology, R versus K lifestyle.
Yeah.
It was beautiful, just how the whole thing flowed. And the R versus K, you guys found a peculiar answer, which was somewhere in the middle.
Yeah, so just to explain this all, so R selection versus K selection uh, has to do with reproductive strategies. So for R selection, you have a whole lot of young, and you hope that some survive. So a classic example of this might be mosquitoes or turtles, uh, or to an extent crocodiles. And then K selection is where you have a lot of investment in one or several large offspring. You have a lot of parental investment. You have long-term parental care for provisioning for the young. And a good example of that would be elephants or whales or humans. We're very K selected. So what we found from our clutch size estimates was that something like a T-Rex would be kind of in the middle. It would have many fewer eggs, we think, given the size of its egg relative to the size of the adult. Many fewer eggs than, say, a turtle, but many more eggs than birds. And there are confounding factors like modern ratite birds like ostriches have a lot of females laying in one nest that one male takes care of. But from what we can gather from the capability of tyrannosaurs at different ages to lay these clutch sizes, um, again, they were somewhere in the middle. So, and this, we didn't sort of take this lightly. So up until the very end, Nick Longrich had some sleepless nights about, gosh, is this really right? We have to look at these regressions again. We have to look at this again. And so our estimates kind of went down a little bit from the initial ones for clutch size. But they're fewer than you'd expect from a 6-ton turtle, but more than you'd expect from even a 6-ton Porosaurus or Deinosuchus or giant croc or something. And so the way that plays into parental care, crocodiles are awesome parents. Crocodiles will stick around, they'll care for their young, they'll watch over their young for a while. They'll guard the nest, they'll keep predators away as much as they can. And then the young will go out on their own, and they'll be more subject to predation and things like that. So a tyrannosaur being intermediate between, in strategy, say between a croc and an ostrich or something like that, might have substantial amount of post-hatching investment in their juveniles, but maybe less than in a modern dinosaur, modern birds, or than in mammals of about the same size.
I grew up in the era of Maiasaura, the good mother lizard, and little Hadrosaur, the little duckbill sitting on their nest and breaking all the eggshell. Histologically, if I looked at the thin sections of what you all did in your Rex versus what their femora look like, would I see a difference in terms of what's going on in the equivalently aged, like 3-month-old taxa?
At 3 months old, I'm not quite not quite sure. You would see in the Maiasaura more cartilage at the ends of the bones. So they were probably a little bit floppy, a little like human babies. Um, and in the T-Rex, the ends of the bones right at hatching would have been very, very well formed. So you also would have seen a lot less cartilage probably right at hatching for the T-Rex. For the baby Gorgosaurus, stay tuned.
Okay.
Bretta Hart is on the case. She has
Nice.
figured it out. So uh, the there's some thoughts out in the literature now as to whether the Maiasaura elements were embryonic or not, or whether they were um, sort of out of the nest. To be honest, my inclination is towards Jack Horner's original interpretation. So I've been wrong before, but I'm waiting for a really thorough testing job to come out with that one way or another.
Can you recap what his original conclusion was?
Great question. Thanks for asking. So because the Maiasaura nestling elements that Jack and Bob Michaela identified um, did not have fully formed ends of their bones, and in the case of the ends of the bones were pretty cartilaginous. And cartilage forms these wild parallel tubes within bone, and it's the Maiasaura embryos looked a lot like that. And you can really tell cartilaginous, calcified cartilage from bone really easily. So these Maiasaura elements had calcified cartilage, and there may have been the ends of the bone that were not fully formed, not fully calcified yet. Um, so Jack's idea was that these bones were from animals that had hatched but were still in the nest. And the original idea was that there was a lot of parental care, and the adults were bringing food to the nestlings. And there's some recent literature looking into all that I'm not as familiar with, and I'll leave it to my colleagues who are on the cutting edge of all that to to get into that, because I'm not really the one to ask. So my inclination is that the Maiasaura were taking care of their hatchlings a little longer, and that the Tyrannosaurs were out of the nest a little earlier.
All of the quail over the last month have been hatching in my backyard and all around the desert where I live. And I think of the quail, they hatch and then they are rolling. I mean, they don't spend any time in the nest seemingly. And there's a bunch, there's a dozen or 2 dozen quail running around. And over the course of a few days, there's not 2 dozen quail running around. There's 12 quail running around. I'm like, but they run quick, just not quick enough.
Yeah, well, yeah. Like outside the room I stay in Colorado, sometimes there was a nest of robins. And robins, when they hatch, are what we call altricial. So they're a little like baby marsupials. They haven't fully formed yet. And the parents are just coming in and feeding them like mad. And in the course of a few days, these little naked robins, grew feathers, and they were quickly out of the nest. So they weren't running around right away, though, like the quail do, or even like ducklings or little baby chicks do. So again, yeah. So Jack's original idea was that um, the Maiasaur were in the nest for a little while, and we'll see how that plays out.
It should be interesting. I'm waiting to see. I wasn't aware people are looking into it again. I'm eager to hear the results to see if parts of my early paleo days get to change. Speaking of tubes and cartilage, this paper is gorgeous. If you like histology or thin sections or cross sections of scanning electron microscopy, this paper's got it all. The colors, there was one image in particular, I looked at it and it reminded me of the Pillars of Creation, that famous NASA poster with the columns. The imagery is what I loved about it is twofold. One, when I see histology, a lot of times I see these little tiny, like look like a tree in cross section, and I don't know what I'm looking at. But yours are so crisp and so clear that you can follow along if you're a neophyte in this area. And with the text accompanying it and a little bit of brain grease, you can get through and see the points y'all are trying to make. And I'm not capable of testing them outright, but they sounded legitimate, but I'm sure others will be hammering against it. So kudos to the illustrations in the paper and the teeth. Oh my goodness. You have wear patterns. And so how do you know that they're not just chewing on something in a nest? Because you argue that they come out quickly and then they're just chomping away at vertebrates. And you mentioned earlier.
That's
But
such a good question. It's so good. Like they could have been chomping on stuff that the parents were bringing them.
yeah.
Absolutely. The clincher again that Brenna Hart is going to establish for everyone is that ligaments between the metatarsals the metatarsals were yanking on each other, and you wouldn't see that with a little in ovo twitching. Um, So I inferred that early on for a bunch of different reasons, and we did some Lara Suring and some colleagues did some awesome histological work and SEM work showing that ligaments were there where we'd expect it. And when I first saw our synchrotron scans, I thought, boy, there are ligaments there. I can see how they're kind of pulling on the bone. And Brenna taught me that I was right for the wrong reasons. It's much cooler than I thought.
Now, that's the student has become the master.
Yeah, Brenda's like she she's now a professor at Pacific Northwest University in Oregon, and it was funny, like Holly Woodward Ballard, like I'm biased, but she's the world's greatest dinosaur histologist right now. So she and I were Brenda's advisors, and Brenda would come to us with these interpretations based on this 3D synchrotron scanning, and as she was telling us, it was obvious, but it's not what we would notice. So we're saying, yeah, okay, yeah, that sounds right. Wow, yeah, oh boy, wow, that really makes sense. So yeah, Brenna just shot past us galactically.
Now, one of the great parts about your paper is the thought experiment that turned into, so you went from a tiny metatarsal to how big would it be in the egg, to how large would the clutch to be, to R to K selection. But there's a chart on there that there's a couple of cloudy graphs that talk about evolution of R versus K, Mesozoic investment in parents across disparate clades. You've got organisms like insects mentioned in this. And my mind was blown. I was thinking, geez, this is incredible.
Well, a way that I think about it, paleontology is a reconstruction of the history of light. And we have evidence for greater parental investment in insects, flowering plants, mammals, dinosaurs, polycotyledonid plesiosaurs. We have evidence for this investment in all these groups in the Mesozoic, and there's no nebulous driving force that's somehow causing everything to go in the same direction. It just this happens to be the time over 150 million years in which you had in multiple lineages the evolution in parallel of this kind of greater parental investment. So you don't have, like, say, R selection morphing into K selection. That's not how it's working at all. Instead, you had in parallel this awesome history, this this mosaic of different groups evolving these sort of different ways of provisioning for their offspring, caring for their offspring, ensuring their survival. Um, so it's as a pattern. The pattern is what we're seeing, and the pattern causes us to go back and look for the process, the parallel processes in all these individual groups. And in every case, in social insects, in flowering plants, in mammals, in dinosaurs, um, there are different and interesting pathways towards these parental strategies. So the history gives us the pattern, and that causes us to visit the processes, visit the evolution in these different groups.
It made me think, and I had never considered it before. I was like, wow, and having the multiple disparate groups showing the same general trend through time was really, to me, a thought argument that, geez, it was really, it made me think, and that's the whole point of it. Now people can hopefully go and provide additional layers of evidence that would suggest that's the case.
And show us that we're full of crap, and
Or
that well, actually, our selection was increasing more than K selection. However, we established the patterns within these groups. That's probably going to hold up. And as usual, Tyrannosaurus is the perfect organism. It's doing things in perfect balance between R and K selection.
So speaking of perfect organism, if you're a little tyrannosaur, our 3 kilogram, 2.5 kilogram house cat sized beast, with I noticed you drew it with tiny little feathers, and it's hopping about. Would an isotope analysis allow us to see if it was eating something different than the adults, or eating the same, or like what you can do with a varanid, supposedly?
Yeah, that's a really awesome question. So we can tell from oxygen isotopes things like uh, how high a trophic level you're eating at, and even what kinds of plants you might be eating, and then what if you're a predator, what kinds of plant eaters you might be eating. Um, so it would be really great to test this out with uh, more ectothermic vertebrates, look at the lizards and turtles and so on that were around at the time, the mammals that were more endothermic, so for producing their own heat internally, look at large dinosaurs and seeing what they were doing. I think someone might be doing that with Tarbosaurus, or probably did it with Tarbosaurus, and I apologize to the workers who might be seeing this who have done it. I'm sorry, I don't remember off the top of my head, but I remember it being really exciting. Um, so we could potentially see what they're eating, falsify our idea that, yeah, they weren't going after insects, they were going after vertebrates. So that's a really exciting direction. What's cool about synchrotron scanning is you can do all kinds of chemical analyses. You can do the fancy, wonderful three-dimensional histology that we've done, but you can pinpoint trace minerals. You can do isotopic analyses. And so you can tell something trophically about the animal's diet, potentially using the synchrotron without necessarily doing traditional uh, histological sectioning and sort of collecting the data from points in a thin section. So it's a great possibility. And Brian is the first person I've heard to suggest that for our little hatchlings. So it's a great suggestion.
And when you ran the scan, did it capture all of that, like on the dual
No,
energy?
not at all. No.
Oh,
Yeah.
so you got to rerun it. And beam time takes a while to get, and it's not inexpensive.
Yeah. Yeah.
Well, I have one last question, and then I'll turn it over to you for any thoughts or things you want folks to know. And that is, on every paper I've ever written, especially when there's multiple co-authors, there's something that usually I wrote that I was partial to that ended up on the cutting room floor because it either wasn't sustainable, they didn't want to have a BC Thinks section of the paper, pure fantasy. That's what the blogs are for, Brian. Did anything get left on the cutting room floor that you wish was in there, or that this is actually you already know this is a two-parter? Brennan's is coming. So is there a third part? Is going to be a trilogy of the little guys?
It's a good question. So things that left on the cutting room floor, I would say that the reviewers caught a lot of our overthinking. And so, and internally, we were all pretty skeptical at everything at every stage. And so through refinement, we ended up having more caveats and basically adding in. Uh, so it's almost like the opposite of entropy. There are a bunch of little scraps on the cutting room floor that we ended up drawing into the edifice.
Wow.
Um, so a lot of that was because we started going for big name journals. And so we had a glorified abstract, you call it, to put everything into supplementary information. And the reviewers often didn't read the supplementary information. And they had a lot of really, really good points. So a lot of us were kind of thinking along those lines already. So we probably spliced more than we cut, if that makes sense. We spliced in more than we cut. I'm trying to think of anything particularly embarrassing that I'm glad we left on the cutting room floor, or that I did. Oh yes, one really, really good. We're so glad here. So fibrolamellar is a kind of bone. It refers to collagen fiber orientation, and it usually correlates with a certain amount of vasculature. And we're kind of using those terms interchangeably. And luckily, a reviewer caught us. A reviewer caught it. And so we're very careful to differentiate between the collagen fiber orientation, how the bone is being laid down, and the amount of vasculature within the bone. So I'm glad that our earlier draft got left behind in that case. So that got left on the cutting room floor, and we spliced in a beautiful edit, a beautiful sort of the perfect sunset shot there into our movie.
Love it. Well, is there anything else about the paper that comes to mind that the world should know that you would like to talk about?
Well, it's a good question. Let's see here. Anything that we want the world to know? We've covered a lot of it already. It's just nice to have this continuity now of for one animal likely, or one a member of one species complex, say Tyrannosaurus, right? Um, we now have it from a sort of yearling to now we have a 3-year-old. We have specimens that are a bit larger. We have supergiant specimens. And part of the trilogy, or part of the dodecology or whatever, is likely to involve locomotion of these animals from when they were very small to when they were very large, and mass estimates of them from when they were small to when they were very large. So my student Kyle Ackett-Weltman is working on that on the locomotion side. My students and collaborators, Jean Q. Eric Duan, Frank Fang, they're working on mass estimates. So we're going to get uh, an ontogenetic through line, hopefully for Tyrannosaurus rex. We actually already have a good one for Gorgosaurus because we have a lot of juvenile Gorgosaurus. We have beautiful work by our colleagues up in Alberta, and now we have a hatchling Gorgosaurus we can add to their list.
Simply amazing. I mean, and if you made it this far, I want to reiterate how one bone can be extremely diagnostic. In the sauropod world, all I need is a certain element in the tail, and immediately you're locked in. There are certain characters that are only in certain taxa, and we've never seen them anywhere else. And we know that's the case because we can take this one little fragment, put it up next to a bigger one that's more complete, and daisy chain our way up. And that's what happened here. Just really lucky. I wonder how many other tiny T-Rex bones are out there, but Nick couldn't confidently say this is a T-Rex. Might be, and there's no mites in this paper. There are, but not on that. I mean, that is the 5 characters you all use are just so clear. I was like, okay, I follow these. That's great. So thank you your team. What a tremendous long marathon to get it published. It sounds like, but you're over the finish line.
Thanks so much, Brian.
It's my pleasure. I'm Dr. Brian Curtis with Fossil Crate saying thank you kindly. Adios.